Hello viewers, hope the first lecture was interesting and useful. So now we'll go to the second lecture. And see new topics, and here the first is about the main parts of a robot. So what are the main parts of a robot? So manipulator is the main part of robot. Probably this term is new to you because generally we represent or we call it as a robo in general, but technically in industry at least it's called as a manipulator. So which is the main body of the robo, and it consists of links, joints and various structural elements. And next is the end effector, which is the part that generally handles objects and make connections with other machines or performs the required task. So again, recollect from the first lecture where I said when you say a robo, it comes without a hand or an end effector. So that's the reason why that is given as a separate part. So let's see what is the anatomy of an industrial robot. So the physical construction of the body, arm and the wrist together is called the robot's anatomy. So the first is the base, which is fixed to the floor or mobile base. So of course, I told in the introduction that the earlier definition of robo where mostly robots were stationary, but later on we developed a mobile robo also. So when I say a base, it could be either fixed to the robo or it could be having a mobile base. So probably here what I would request you to assume is the base. Consider the hip portion of a human body or your waist portion of your body as the base. And next is the body which is attached to the base, probably your upper part or the part above your waist is considered as your body. And the third is your arm, so which is attached to your body is your arm. And then the fourth is the wrist, which is attached to the end of the arm. See again, up to your the wrist, there is no flexibility, there is only movement. You cannot have any flexibility with your hand. So with the wrist we add flexibility to your arm. So now probably we'll have a comparison here. This is what I was mentioning about. So you consider the waist as your base, and typically analogically here you have the waist or the base of the robo, and you have the body here. Of course, in a typical industrial robo you cannot have something typically as a body. Instead you have the arm. So the whole portion is your arm, and comparing with your human one, this is your shoulder, and this is your shoulder, and this is your elbow. So this is your elbow joint, shoulder joint, and this is what I was mentioning about the wrist joint where it gives some movement. So this is the basic anatomy of a robo. So next is, of course, I have a hand. So of course there is a joint, bones, all those things are there. But can I move my hand, right? So I need certain accessories to move my hand. So what are those things? Say for example, my brain, it gives some signals to my hand, and the brain says move your right hand or stretch your hand. So when I need to stretch, how do I stretch? So I do have my muscles, nerves and all those things. So the brain gives commands, the muscles which has the strength, right, it gives some force and movement to my hand. So probably when I say hand, you just assume only the bone and joint there, and when I say accessories, the brain, the muscles, nerves, all those things are accessories. So similarly, you have the physical structure of the robo, but you need certain accessories to actuate or make the robo work. So what could be those accessories? So let's see one by one here. The first is actuators. As I told you, the muscles of the manipulators, like we have muscles, these actuators are called the muscles of the robo or the manipulator. So how do I actuate, or what are the different means by which I can power my arm or the manipulator. So we have stepper motors, servo motors, or be pneumatic or hydraulic drives which could act as actuators to give movements to my arm. So next is sensors. Of course, when you compare it with human, so things are being done automatically. As I keep moving my arm, the brain, the eye is the vision system here. It automatically senses the movements, and the brain knows whether I have reached my target or not, and it gives additional signals or commands. Whereas in case of a robot, sensors are very important because they collect the information about the internal state of the robot or to communicate with the outside environment. So we have a vision system, a touch sensor, and a tactile sensor. So all those things are there. And the third is the controller, which is the one which coordinates all these activities. So it controls the motions of the actuator and coordinates these motions with the sensory feedback information. So for example, I have put a sensor. The sensor gives me a signal. And what do I do with the signal? So using that signal, I need to give some corrective actions to the robot. So then, say for example, I need to reach to an object. So I stretch my hand and I'm not able to reach it. So that signal goes to my brain, and the brain says, why don't you stretch forward so that you can reach to your target. So some corrective action is being done. So similarly, in case of a robot, when a sensor gives some input, the control must be able to process it and then give some alternate signals to that. So that's the role of a controller. So next comes the end effector, or what we call it as a hand. Now when I talked about the main parts of the robot, I said the manipulator and the end effector. Whereas when we talked about the anatomy, I didn't talk about end effector. I only stopped up to the wrist. So because the hand or the end effector is not part of the anatomy. So this I am giving a lot of emphasis because you need to keep in mind, when you buy a robot, you get without a hand or an end effector. So next is about the classification of robots. If you recollect my first lecture in the introduction, we discussed about, and there could be different types of robots. So when you say different types, it could be the variation in the structure or the design, or the variation could be in the way the robot functions or the way the robot works. So let's see what are the various classifications of robots. So the first classification is based on the type of system, how actually the robot works or functions. So in which we have a point-to-point robot system, and then we have a continuous path robot system. Of course, the subsequent slides we will see in detail about all these things. And the second type of classification is based on the control loops or the control system. Let's see what are the different types. The one is the open loop control system, and the second one is your closed loop control system. And there is another category based on which we can classify the robots. It's based on the type of the coordinate system based on which the robot structure is designed. So this also we'll see in the subsequent slides. So first is the point-to-point system. So what do we do here? So each axis moves from one point to the next as fast as it can. That is, path is not controlled. So basically, when I say point-to-point system or a point-to-point robot, I need to move from one point to the other point. How fast I can move. The path is not controlled. What does that mean? So whether I move along a straight line, whether I take a circular path, whether I go step path, triangular path, it's not of concern. So my objective is move from one point to another point. So that's point-to-point system. So time for the longest axial motion is calculated. See, when there are so many joints, say even here we have upper arm, the forearm. So time for the longest axial motion is calculated as time t. Say for example, I move this my upper arm through a small angle, whereas my forearm moves through longer angle. So what is the longest time for moving this? So that is calculated as time t. Velocities of other axis is based on t. So now what I do is I take this t as fixed, let's say 10 seconds. So for moving from this position to this position, that is the longest distance it takes, time t. Whereas the movement of my the upper arm, for that also the same 10 seconds is calculated. See, let's assume I am rotating my upper arm through 30 degrees, for which it takes 10 seconds, right? Whereas the upper arm, I am moving it only through 10 degrees, whereas I am giving the same time of 10 seconds. So means what? The speed or the velocity of this and the velocity of this is different. Right? This moves at a faster rate, whereas this moves at a very slow rate, because for that 10 degrees of movement, it should take 10 seconds. Right? So this is the basic idea here. The time taken for all the axes are same. So depending upon the distance it has to move, it has to adjust the velocity. So t is same for all axes. Motion in all axes terminate simultaneously. So, so I told you the time is same 10 seconds, whereas the velocities are different. So when I move my hand from here to here, so once I reach the target, all the motion should be stopped. It's not like one arm has reached its position, the other arm is still keep moving. So that should not happen. When the end effector, let's assume, reaches the target, the motion of all the axes should stop. So that's what you mean here. A motion in all axes is terminated simultaneously. The trajectory is arbitrary. That's what I told in the beginning. Objective is to move from one point to the another point. Which path or the trajectory is not important. So what could be the example for this? What is the application for a robo where it moves from just one point to another point without concern about the point? So spot welding. So you need to make spot welds at two locations, and from here to here, how do I move? Go like this, go like this, or go like this? It's not of concern. Only thing is I need to go from this point or this coordinate points to this coordinate point. So now this diagram you can see. So this is my starting position and this is my target position. So of course when you look at the shortest path, this is my shortest path, but there could be some other constraints where because of which I move here and go like this, or I go through this point. So this is about point to point system. So next is continuous path system. Means the path, of course, here also you have the starting point and the ending point, but the path is continuous or continuously monitored. So that is the continuous path system. So all axes move simultaneously, each at different velocity. So same thing happened in the previous case also. Of course, the one difference which we can differentiate between point to point and a continuous path is, in case of a point to point system, one axis will move at a time, right? So the movement is either in x-axis alone or in y-axis alone. So when that system is there, what is the advantage? I move only one axis at a time. So when I move the x-axis, only the x motor rotates, the y motor doesn't rotate. When I move in the y-axis, only the y motor rotates. So means the control system is very simple because only one axis is activated at a time. Whereas in case of a continuous path, all the axes are moving simultaneously. So velocities are coordinated under computer control. So time of motion is different for each axis. So again, we'll go back to the point to point where we said the time is same for all the axes, and the velocities were different for different axes, right? Whereas here velocities are different and the time is also for different axes. So now you can find out the complexity in the control system, right? Example, spray painting and arc welding. So now again, to differentiate between point to point and continuous path system, probably I want you to rewind back, go to your workshop where you worked on a typical lathe. So the operations like turning and facing, when you do the turning operation, you move only along the Z axis, or you rotate only one wheel. When you want to do the facing, you move only one direction, the other only one wheel is rotated, right? So turning only one axis, facing only one axis. Now if you want to do a taper turning operation, so what you have to do? You have to control both the wheels simultaneously so that it takes an inclined path, right? So that needs high level of coordination, eye and hand coordination to do that. Because it's a little difficult, so that's the reason why you add a taper turning attachment. Or if you want to do a spherical turning, there also you need to control both axes simultaneously, which involves a lot of eye to hand coordination. Of course, eye, hand and your brain, of course, which gives you the commands. So typically here also, when you move one axis at a time, the control system is simple. Whereas when you want to control more than one axis simultaneously, let's assume if it's a two axis, it's X and Y motors rotate simultaneously. If it's a three axis, X, Y and Z motors function simultaneously. So then the control system becomes complicated. So when I say spray painting, if it is a flat wall, yes, I just keep move my spray gun only like this, in one axis. If it is a curved path, so I have to control it like this. So that's the difference between a point to point and a continuous path system. So the examples of spray painting and arc welding. So this is what I was mentioning about from here to here. Yes, it is a straight line. Whereas when it moves along this curved path, both X and Y axis motors have to move precisely controlled. And here it takes the inclined path, where again both X and Y motors have to work or rotate simultaneously. So this is about next is open loop control system. So control is given to the individual axis. Of course, I know it could be hydraulic, pneumatic, whatever it is. I give the control and say that move through, say 30 degrees, right? No feedback is obtained. So it's a one-way communication, right? The controller says so many pulses and your forearm must move through 30 degrees. So that is the control given. It doesn't bother whether it has gone through 30 degrees or not. So that is open loop control system. So it is mainly used for loading and unloading applications. Say for example, when I say move through 30 degrees, let's assume that it has stopped short of 0.5 degrees. It moved only through 29.5 degrees. Or it went past 0.5 degrees, that is it went through 30.5 degrees. So there are applications where this 0.5 degrees is not very critical. Say applications like loading and unloading applications. It takes a part, puts it into a box, where that 0.5 degrees is not of much concern. It's not very critical, right? So there I use open loop control system. So this is what I was saying. This is a control unit which gives signals or pulses. It goes to the driver and then it drives the motor, assuming that 30 degrees it has achieved one. And second thing is, even if there is a small error of say 0.5 degrees, my objective is met. So when every time we talk about accuracy, why do you want to compromise on the 0.5 degrees? Why can't I go for an advanced control system where it exactly travels to 30 degrees, right? So as I told you, when you want an advanced control system, it becomes costly. right? So I go in for open loop control system, which is very simple in terms of design. In terms of cost, it is very less. Still, it serves my purpose. But there are applications where precise movement is needed. Say for example, I need to do an assembly, put my piston into the cylinder, for example, right? The axis of the cylinder, the axis of the piston should be exactly aligned so that I'll be able to insert it properly. This is one case. And the other example which I talked about spray painting on a curved surface. So the distance between the surface and the spray gun has to be maintained constantly, and also the path should be perfect. The distance between the spray gun and the surface, painting surface, should be maintained uniformly so that the painting is done effectively. So such applications, accuracy is very important. So when I say move through 30 degrees, it has to move exactly 30 degrees. So how do I ensure that? So to ensure that, I need to get a feedback. As I told you in the beginning, I put a sensor, get a feedback, see whether it is short off or it has gone past. That corrective signal is given back, and the robot adjusts its hand and ensures that it traveled exactly through 30 degrees. So that is where your closed loop control system comes into picture. Right, so control here also, control is given to the individual axis. Feedback is obtained through sensors. Right, I think now when you understand the importance of sensors. The corrective signals are sent by the control unit. So this is a simple schematic sketch of the closed loop control system. So there is a reference, and this is the controller which gives the input to the system, and there is output, and this output is measured through a sensor, and the sensor gives the output here. Now what happens? The output of the sensor is compared with the reference signal, and an error is found out. The error could be plus or minus, as I told you, if it is 29.5 or 30.5, right? So now the error is measured and the corrective signal is sent back, so that finally the system output gives me the exact movement of that, right? So this is a closed loop control system. So we have come to the end of lecture 2, and in this lecture we have seen the various topics like the main parts of a robo, and what is the anatomy of a robo, and what are the various accessories needed to make the robo function properly, and classification of the robo. And under classifications there are 3 types actually, and among those 3 types we have discussed about the classification based on the type of the system, and also the classification based on the type of control system. So thank you for watching this, and I'll see you soon in the next lecture. Thank you.